In this video, we're going to return to the real numbers now. We've spent the last couple of videos just going over some preliminary content. Now we're in the position where we can move back to actually understanding what the real numbers are and how we can characterize them. So to start with, we're going to assume that the real numbers are an ordered field. So this is just going back to what we did a few days ago. Real numbers is an ordered field. That means everything involving inequalities is going to work on the real numbers, just like it did with the rationals that we developed earlier. And everything we can do with rationals, like multiplying and dividing and adding and subtracting, that's all going to work too. So it's going to be containing Q. Let's just try writing that again. Containing Q as a subfield. Okay, so that means all our inequalities work. Addition, subtraction, all that kind of stuff is all going to work. Just like it does for the rational numbers. Okay, so as in and of itself, that's not enough to define the real numbers just by making the rational numbers a subfield of it. We need something unique to characterize the real numbers that addresses the problem that we had with our rationals, which was that there were gaps in it. There were some numbers, and we showed that there couldn't be a rational number that was the square root of 2, for example, and we need to define our real numbers in such a way that things like the square root of 2 will exist, and there are no gaps in our number line. And the way that we do this is to use the axiom of completeness. Now this is an axiom. It means that essentially it's an additional piece of information that we're adding to our real numbers. It's not something we're going to prove. It's something that we're enforcing on them. And the properties of the rationals that we took from before and the fact that the real numbers have them contained in it, together with this axiom, is enough to define what our real numbers are. So this axiom says that every non-empty set of real numbers that is bounded above has a least upper bound. Now we haven't defined all of this language just yet, so before we look at this more closely and see what it means, we better define what these things about bounds actually mean. So let's take a look at what boundedness means. Here's our definition. Imagine you have the number line, the real number line here, and you've got some set on it, which is just some subset of the values. Okay, here's our set A. Essentially, the idea of a bound is just a number such that everything inside my set A is less than it. That would be an upper bound. So if I were to go here, this number B is an upper bound because every element of A is less than it. Similarly, this is also an upper bound, as is this. So we've got this concept of upper bounds, and similarly we've got lower bounds down here, so I could define some lower bounds on the other side. Let's call this one L. This is the lower bound. Every element of A is greater than or equal to this lower bound. So you can see that I could move these lower bounds around and make new ones. Okay, we can have lots and lots of different lower bounds. So the next slide is going to be specific about the fact that there are things that we can look for the least upper bound for a set, or the greatest lower bound for a set, and give some special meaning to those. So a least upper bound is basically an upper bound but has an additional property. So we define the least upper bound for a set, which is also called the supremum. And we define it to be the least upper bound if it satisfies two conditions. First one is kind of self-evident. If it's a least upper bound, it definitely must be an upper bound. Okay, so it has to be an upper bound. That much makes sense. And it also has to have the property that it is less than or equal to any other upper bound that we could find for our set. So if you remember that map we drew on the previous slide with the number line and the bounds, our least upper bound has to be less than or equal to any other upper bound. So I'll just highlight a little bit of terminology here. So the least upper bound has another name, the supremum. And similarly, we have the greatest lower bound, and that's known as the infimum. Okay, so we'll often be referring to inf A or sup A. and that's what we mean. Here's the definition of those. So let's just make a few, let's just take a couple of example sets and see what we can say about bounds of these sets. So for the first set, we can make some statements that are true. First one, we can say that 10 is an upper bound for S1. Okay, S1 is all numbers between 3 and 7, or negative 3 and 7. 10 is greater than every element in that set, so 10 is definitely an upper bound. Likewise, 7 is an upper bound. Okay, upper bounds are not unique. We can come up with lots of different ones. The thing that is unique is the least upper bound. So the supremum of S1 is going to be, just take a second to think about that, it's going to be 7. Okay, we can also say that S1 is bounded above and below. Bounded just means there exists an upper or a lower bound. So if I say it's bounded above, it means I can find at least one upper bound for it. Similarly, bounded below means at least one lower bound. You could just say S1 is bounded, and that encapsulates both in one. Okay, so if we look at lower bounds, doing the same kind of thing, -6 is a lower bound for S1. And we can move across and find the greatest one. -3 is also a lower bound. And just to practice using the terminology correctly, we can say that the infimum of S1 is equal to -3. Okay, so here we also have that the inf S1 is an element of S1, and also the supremum of S1 is also a member of S1. But this is not necessarily the case. If those inequalities had been less thans, rather than less than or equal tos, then the infimum and supremum would have been the same numbers, but they would not have been members of the set. So note that this is not the case. Not always the case. So if we look at set S2 now, what can we say about that? Well, let's try and find the supremum and infimum of this set. Okay, so supremum of S2, we're looking for the biggest, the smallest number that is an upper bound for S2. Now you can see as we start plugging in natural numbers, starting at 1, our sequence is going to go 4, 3 1/2, 3 1/3, 3 1/4, etc. So our supremum is going to be 4 in this case. And our infimum is going to be 3. Now we'll develop some machinery that enables us to prove this properly, but hopefully it's fairly intuitively obvious that as n gets big, I'm going to get closer and closer to 3, but I'm never going to quite get there, and our greatest lower bound is going to be 3. So we can say that for this set, supremum of S2 is in S2, but the infimum is not. So you've probably been thinking, this is very much like maxima and minima. So let's quickly define what maximum and minimum is. So a maximum of a set is an element for which it is bigger than or equal to every other element of the set. Now the difference between maximum and supremum is that the maximum is an element of our set A. Supremum is not necessarily, sometimes it is, sometimes it isn't. Maximum has to be in the set. This means that some sets do not actually have a maximum or a minimum element, and some do. So let's look at an example real quick. This will be example 4.5. If we look at the interval 0, 2, what can we say about that? No maximum. Okay, 2 is not in the set, and we can get as close to 2 as we like. So there's no actual largest value in this set, no minimum, but we do have that the supremum of our interval equals 2, and the infimum of our interval is equal to 0. If we look at the closed interval version of this, now we're including the endpoints, we have max of 0, 2. Now 2 is actually included in the set, and so that equals the supremum, which equals 2, and the infimum of the set, the minimum, not the infimum, is equal to the infimum, okay, so that's interesting. We have our maximum and minimum actually being members of the set now, and the supremum and infimum of the set are the same as they were before. Okay, so if a maximum of a set exists, it's also going to be the supremum, but you can have a supremum and no maximum. So we can set up a number of useful theorems that make it easier to work with these infima and suprema, especially when we have sets that are maybe shifted by a constant or multiplied by a constant. So here's an example of one of these such theorems. I think it's theorem 3.5.2 in the reader. So we have let A be a set, that should be a capital A, and the real numbers that's non-empty and bounded above, and we've got some positive constant C. And we're defining our set little c times our big set A as just the set of all the elements of A multiplied by C. So just take a second to make sure you're comfortable with what that set here actually means. We're taking all of the elements in our set big A, multiplying them by C, and that's our new set C times A. Now the theorem statement says that the supremum of CA is equal to C times the supremum of A. So if we know sup A, then we can get sup CA automatically. Alright, so how do we prove this? Well, we have to show that the supremum of a set is equal to a particular number. Okay, so we have to show that this number C sup A satisfies the two requirements of supremum of this set C times A. Okay, so if we look at our definition, part 1 says verify that C sup A is an upper bound of CA. Okay, so we've got to show that this number C sup A isn't actually an upper bound for our set. And the second part, remember, is to show that it's the smallest of these. Okay, so we need to pick an arbitrary element of our set CA and show that C sup A is greater than or equal to it. So an arbitrary element of our set CA looks like this. Let CA be an arbitrary element of CA. Now we need to show that C little a is less than or equal to C sup A. And we're going to use the fact from our set A that the supremum is greater than or equal to every element and just shift that by multiplying the inequality by C. We know that A is less than or equal to sup A. That's by definition of supremum. So it follows that CA is less than or equal to C sup A. Thus, C sup A is an upper bound of CA. That's good. So if we go back to our supremum definition, part 1 was to say that to show that our number actually is an upper bound. Part 2 is to show that it's greater than or equal to, less than or equal to any other upper bound. So part 2 need to verify that C sup A is less than or equal to B for any upper bound B of CA. Okay, so has to be true for any upper bound B, so we start in the typical way and we just pick one out. So let B be an upper bound of CA. Okay. What we're going to do next is we're going to transport our elements from CA into A, because our statement about the supremum is something that we know about A at the moment. We're trying to prove it about CA, but we know the supremum properties currently hold in A. So that will explain why I'm about to do the following. So let A, little a, be an element of our set A. Okay, so I've taken an arbitrary element of our set A because I intend to use the supremum property of it somehow. It follows then CA is an element of C big A, and so CA is less than or equal to B. Okay, because B is defined to be an upper bound of CA, and so CA has got to be less than or equal to B. Thus, we can take that inequality and rearrange it so it's a statement about A instead of a statement about CA. Thus A is less than or equal to B over C. That's because C is greater than 0, so we can multiply by 1 over C freely using our inequality properties. And hence, A was an arbitrary element of our set A, that's why I chose that first, and it's less than or equal to B over C, hence B over C is an upper bound for A. This means that our supremum of A is less than or equal to B over C. Remember, supremum is just the least of all upper bounds. We've just shown that B over C is an upper bound. And now we can multiply our inequality through by C, and hence we have a statement C sup A is less than or equal to B. Okay, so when I multiply through by C now, I've shown that C sup A is less than or equal to B. Remember that B was a arbitrarily chosen upper bound of CA. So C sup A is less than or equal to it, and so we've already established that it was an upper bound in the part 1 of the proof. We've now established that it's less than or equal to any other upper bound, thus our theorem is true. The supremum of CA is C sup A. And we can do many similar things. For example, we can, instead of multiplying by C, we can add C, and we can prove a similar statement for C, the supremum of C plus A. So proof, I'm not going to go through and prove it because the structure is almost identical to the previous one, so we'll just leave that proof as an exercise. So next up, we've got a pretty useful theorem, which is the way to interpret a theorem like this one. It's an alternative characterization of the supremum. So we've established the setup for the theorem is that S is an upper bound for a set A, and then we've got S equals sup A if and only if for every choice of epsilon greater than 0 there exists an element A satisfying S minus epsilon is less than A. So just if we're kind of taking a zoomed out look at this for the time being, this is an if and only if proof, which means that the statements on either side of the if and only if have got to be logically equivalent. So what we're really setting up here is an alternative characterization of the supremum. So we're showing that the definition on the right, if you like, for every choice of epsilon there exists blah, is going to be equivalent to S as the supremum of A. Okay, now to prove something like this, it's an if and only if, so we've got to prove both directions. So one direction is often a lot easier than the other, and we'll start with that one. So we'll go for the forward direction proof, which is to assume that S is the supremum and then show the other part follows quite naturally. So for the forward part of the proof, we'll let S be the supremum of A. Now we've got to show for every choice of epsilon something is true, so we'll choose epsilon to be an arbitrary number greater than 0. Okay, so just note this is a very common template for a proof. It says that for every choice of epsilon something or other must be true, so we're choosing an epsilon and we've got to show that what follows has got to be correct. So in this particular case, we've chosen our epsilon, and now we'll just show that we'll consider the number epsilon, the number S minus epsilon. This is not an upper bound. Remember, S is our least upper bound, so S minus epsilon cannot be an upper bound. This is not an upper bound for A, which means, okay, if something is not an upper bound, it means there's an element of the set which is larger than it, so which means there exists my E keeps disappearing. A in A such that A is greater than S minus epsilon, which if we rearrange that becomes S minus epsilon is less than A, which is what we were trying to show. Okay, so we've chosen, just double check we've proven the right thing. We've assumed our left-hand statement, S equals the supremum of A. We've chosen an arbitrary epsilon, and we've shown that there exists an element A such that S minus epsilon is less than A. This is going to work for any choice of epsilon, and so we're all good. Notice that this is going to work for any choice of epsilon. The A that exists might be different depending on what epsilon is. That's the normal way these work, but we've proven one direction. Now it's not enough to just prove one direction if it's an if and only if theorem, so we have to supply a second proof, which is the backwards direction. So now we have to assume that there exists, for every epsilon greater than 0, there exists an element A satisfying blah. We have to show that that implies that our element S is the supremum. Okay, so let's just set this up. So we're just going to suppose the statement following our if and only if. So suppose for every choice of epsilon, there exists an A satisfying S minus epsilon is less than A. Okay, we now have to show that S is the supremum, and this time we're going to do this by contradiction. So we're going to assume our hypothesis and the negation of our conclusion. So we'll assume that S is not the supremum and see what happens. So assume S is not the supremum. Now we need to translate that into a more useful statement, in which in our case will be, if S is not the supremum, there must be an upper bound for A that is less than it. So let B be an upper bound for A with B is less than our supremum S. Okay, we're now going to find our contradiction by making a particular choice of epsilon, which is going to lead to a violation of something. So I'm going to choose my epsilon to be S minus B. Okay, we're assuming that B is an upper bound which is less than S, so epsilon is a number that's greater than 0, and thus from our hypothesis here, there exists an A satisfying S minus epsilon is less than A. Thus there exists A and A satisfying S minus epsilon is less than A. Now S minus epsilon here is just going to be, well, epsilon is S minus B, so S minus epsilon is going to be B, so that implies that B is less than A. But A is an element of my set, and B is supposed to be an upper bound for it, so B cannot be, it cannot be an upper bound for A. Okay, so we made an assumption that violated the supremum. We assumed that B was an upper bound for A with B less than S. Okay, this is not going to be true if S is the supremum. And we're trying to show that S is the supremum. So we've assumed something that contradicts that, and then we've done some processing on it, and we've found something that's not true, which is we made it be an upper bound, but then we found there was an element of A that was bigger than it. And so our assumption is therefore incorrect, and so this element B cannot exist. Hence, let's get the right color. S is actually our supremum. And now we've proved our theorem both directions, and so overall our theorem is true. This means we've now got an alternative way of characterizing supremum, which might be useful. So maybe we've got a theorem that involves a supremum, and that means we can invoke this right-hand side part of it, which says that for every choice of epsilon, it might be useful to set up a choice of epsilon, and that will give us an element A that we want.